Good day to all of you. So, we continue from where we left off in the last class. We had been discussing about state space representation of DC-DC converters. We had split the DC-DC converter into two parts. The first part, or the first mode, wherein the one part of the switch is on, the other switch is off, and one part of the circuit is operative, and when the other portion of the switching time, that is 1 minus dt portion of the switching time sets in, the second part of the switch is operative and the first part, the earlier part, is disabled. So, this is what we had used for formulating the state space equations for the two parts of the circuits. And now we need to combine them into a single averaged state space model, which takes care of both the situations. So, we continue from there, and let us title this course as circuit averaging method. So, this lecture, let us name it as circuit averaging method. Basically, what it does is it tries to average and bring in the values of the states as represented in the dt time period, and those that are represented in 1 minus dt time period together into a single averaged state space model. So, therefore, we had this portion of the circuit. We had taken the example of the buck converter, wherein we had in the first case a switch S1 and an inductor as shown here with the load R. So, this is the first part of the circuit where we have not switched on the second switch S2, only switch S1 is switched on, VG, L, C and R. And in the second part, we have only the switch S2 which is switched on, as shown here, and VG is effectively removed from the circuit. So, this is the second part, and we know that this part and this part together, this is time, together forms one switching period. This is one switching period T or TS. This is one switching period, and it is split into two mutually exclusive parts. This is D TS and this is 1 minus D TS. Okay. So, where D is the duty ratio. Now, these two portions of the circuits are operative at these points, and we had also developed the state equations for this portions as follows, which is IL dot and VC dot. So, this has a matrix like that, IL and VC plus the input matrix where the input is VG, where in this case it was 0 minus 1 by L, 1 by C minus 1 by RC, 1 by L and 0. Likewise, for this case, IL dot VC dot, which is equal to a matrix A matrix multiplied by the state vector plus the B matrix multiplied by the input vector VG. Now, we had seen that there is no input coming through to the output in this case, that is 0, and this is minus 1 by L, 1 by C minus 1 by RC, this remains the same. So, these two are the two state equations for the two modes, and the output equation, we said the output is V naught equals 0 1 IL and VC, the state vector, plus 0 and VG. Likewise, similarly, you have 0 1 the state vector IL VC plus 0 VG. So, this much we had covered in the last class. We had developed the individual circuit mode state equations. This portion is the state equation for mode 1, this is the output equation for mode 1, state equation for mode 2, output equation for mode 2. Now, here two things I would like to mention. One is on the variables that will undergo a slight change. I will come to that one. And the second point is that we shall combine both this portion and this portion into a single equation. Now, before we do the combination, let us take the case of the variables first. Now, look at the variables here. We are using the uppercase D, and so also here the uppercase D. I am going to erase that and erase this and change it into lowercase d, 1 minus d. So, it becomes this portion of the period becomes dTs, where d is lowercase, 1 minus dTs, again d is lowercase. Why did we do that change? So, let us revisit some of our earlier concepts to know why we are doing this specific change. If you recall, much earlier we had a transfer curve y versus u, and this transfer curve had a nonlinear shape like this. And now, let us say this is the operating point. And this operating point is the nominal position of the u variable and the y variable, input and the output variable, and it could have a variation about the operating point in the neighborhood of the equilibrium state. Now, this is our equilibrium state. Equilibrium state, or in other words, steady state. Steady state. Now, this steady state portion is having a nomenclature operating point u, uppercase U and y, and any deviation about the operating point we are calling as u hat. Any deviation about the operating point we call it with the small lowercase variable and a hat. So, equivalently, if you look at any typical inductor current waveform in a buck converter. So, in the buck or the DC-DC that converter that we saw, if you look at the time domain evolution of the inductor current IL, it would appear something like this, let us say, goes through the transient and comes into the steady state like this. When you zoom in, to the waveform, it would appear slightly different because you are looking at the switching. So, let me put the dotted to indicate an average effect like that, and let us see that during dt it will rise, during 1 minus d it will fall, during dt rises, falls, so on, keeps happening in this fashion. So, this would be the wave shape of the inductor current. So, if you look at this portion, we will call that one as the equilibrium or steady state part, equilibrium or steady state part. Capital or uppercase symbol. And if you look at the deviations about the steady state, that we will have the symbol, we will call it by lowercase symbol with a hat, and the actual large signal, instantaneous large signal IL, which is just plain lowercase, will be the uppercase symbol, the steady state part, plus the small signal part, that is the hat part. So, if you look at it, this is the actual large signal value. This uppercase signal is the steady state value, and this lowercase signal with a hat on top is called the small signal value. So, every variable in the physical system has these two parts. So, if you consider the variables like u, d, the state variables in our case is 2 in number. You have IL and Vc and the output variable. All these variables have two parts, a steady state part plus a small signal part, wherein the small signal deviation with respect to the steady state part is very much less than 1. So, very small deviation about in the neighborhood of the steady state or nominal operating point. Likewise, the duty cycle large signal value has a steady state part indicated by this uppercase d plus a small signal part lowercase d. D hat by d of course is much less than 1. Likewise, the states, you have the steady state part and the small signal part. And the output, which has a steady state part plus the small signal part, wherein y hat by y is much less than 1. So, likewise, every signal has these two parts. This is very small compared to the steady state part. So, that is the criteria. So, now that is why I have replaced the symbol d with the lowercase d, indicating that it is the large signal value, which comprises of two parts, steady state part plus the small signal. So, to bring in this change in notations, I have replaced the symbol for duty ratio with uppercase d to lowercase d, and so also here consciously, so that what we do in the future equations, to bring in clearly the distinction between the steady state part, the large signal part and the small signal part. So, now coming back to our model, we have the two models, which now I will compactly write it as x dot, which is equal to a1 x plus b1 u, y output, which is equal to c1 x plus d1 u. This is the model for the first part, the first mode of the circuit, when the switch S1 is on during the period dTs. During the period 1 minus dTs, we have a2 x plus b2 u and y equals c2 x plus d2 u. So, this is happening during the time d Ts, and this was the result of what happened during the time 1 minus d Ts. And remember that this portion of the state equation is nothing but this state equation and the output equation put together, and this state and output equation during 1 minus dTs has been indicated like this with the subscripts A2, B2, C2, D2. Now, we need to combine these two together to obtain x dot, which is equal to Ax plus Bu, y equals Cx plus du. So, wherein this A is the weighted average of A1 for a period d dts and A2 for a period 1 minus dts. Likewise, B is the weighted average of B1 for the period dts and B2 for a period 1 minus dts. Likewise, C is the weighted average of C1 and C2, D is the weighted average of D1 and D2. Now, if you take the equation x dot, which is equal to A x plus B u and y is equal to C x plus du, A, as we said, is nothing but A1 into D plus A2 into 1 minus D. The weighted average of these two. B is B1 into D plus B2 into 1 minus D. Similarly, C is C1 into D plus C2 into 1 minus D. D is D1 into D plus D2 into 1 minus D. So, this is how the weighted average is taken into account. As we saw that we are trying to average the signals x and u with respect to the periods d and 1 minus d, as we saw in the last class. And we are taking the weightings into the coefficient matrix to so that the same states as indicated in period dt and 1 minus dt will be used here. We are not changing the symbols for the states and the input vectors. Only the weightings has been taken into the matrices, into the A, B, C, D matrices. So, now you must note that the A, B, C, D matrices being weighted by D and by virtue of the fact that D is the duty ratio, which keeps changing with time based on the controllers which are employed to control the output y. The matrices A, B, C, D would become time varying matrices, because D is no longer a constant. This is one issue that we need to address and solve, because the state equation methodology that we will be adopting for designing the controllers are for linear time invariant systems. So, the matrix A and B are supposed to be constants. So, coming back to this equation, this weighted or the averaged model together is called where both the A1 part and A2 part are brought together, is called the average large signal model. So, we began with the large signal model, which is this. This is the large signal model, So, also this, also the large signal model. These two have been combined together by weighted averaging, and this is called the averaged large signal model. Okay. So, now we further reduce it to take care of, there are two issues, non-idealities which will creep in, just see that that is one major issue, together with the fact that the A and the B matrices are no longer constants, but time varying matrices, and these are also to be addressed. Now, if you look at the equation x dot, which is equal to A x plus B u, these are all large signal values, these are all large signal variables. Now, we replace them because we know that x is nothing but steady state part plus small signal part, u is nothing but steady state part plus small signal part, and so on, all the variables. So, we will replace it with their split parts, dot equals A into the state plus B matrix into the input variable. And this itself, A and B itself, can be written as these. So, if we rewrite them by splitting them into the steady state and the plus A2 1 minus D multiplied by steady state plus B1 D plus B2 1 minus D into steady state and small signal part. So, this would be the equation of this average large signal model expanded. So, let us now simplify it a bit further. And in the process of simplification, let us make some small assumptions, valid assumptions. We said that the steady state part is very large compared to the small signal part. Small signal part is very small compared to the steady state part. And therefore, if you have a term which is multiplication of two small signal part, okay, then we can neglect this term, because x hat itself is very small compared to x. So, in the normalized form, a very small number less than 1 into a very small number less than 1, we are trying to neglect it, that it is not so too significant. And this is the first assumption. And in the second, the steady state part or the equilibrium part is reasonably steady, and therefore, dx by dt is equal to 0 for the steady state part. So, it does not have a slope, it is like a constant dc. So, therefore, x dot, which is equal to ax plus bu, can be equal to 0. So, this is the second assumption that will come into the picture. Now, using these two, you can apply simplification rules for this, and observe here that we have this d. Now, this d you should further expand it as d plus d hat, and this would become 1 minus d hat. Likewise, here you have d plus d hat, and this would become 1 minus d hat. So, you have d hat term, product of x hat d hat, product of d hat u hat. Now, all these product terms you can delete, you can remove, neglect, and then apply a x plus b u equal to 0, assuming the steady state deviation of the state vector is 0, dx by dt, and using that you will obtain x hat dot, because the steady state deviation is 0, you only have x hat dot on the left hand side of the equation, which is equal to a x hat plus b u hat, all are small signal quantities, plus a1 minus a2 steady state quantity x plus b1 minus b2 steady state input quantity u. Now, this whole is multiplied by d hat. So, observe that you have small signal state, small signal input, and the small signal duty cycle. This forms the control input in most cases of our DC-DC converter. Likewise, we could in the similar manner take the output equation, replace it with y plus y hat, which is equal to C1 d plus C2 1 minus d x plus x hat plus d1 into d plus d2 1 minus d u plus u hat. So, this can be simplified, and on simplification for the small signal you have y hat, which is equal to C x hat plus d u hat plus C1 minus C2 x plus d1 minus d2 u. This whole thing product d hat. Observe again the same form, you have the small signal terms coming in, and you look at this is the dynamics of this state matrix A and B. They do not contain any small signal varying term. At most they would contain only the steady state terms, which for a given operating point is constant and fixed, and therefore they can be used for controller design in the linear time invariant mode itself. So, now let us apply our case to the DC-DC converter, and we had taken up this buck converter, DC-DC buck converter, and let us try to apply the process. Now, the consolidated averaged model for the DC-DC converter is of this form. I will call that one as the averaged model of buck converter First, let us see A. A is nothing but A1D plus A2 1 minus D, which is nothing but in this case 0 minus 1 by L 1 by C minus 1 by RC into D plus A2 is also same as A1 in this case, in this specific case 1 by C minus 1 by RC into 1 minus D. So, this will turn out to be as D plus 1 minus D is equal to 1. We will have A as nothing but same as 0 minus 1 by L 1 by C minus 1 by RC in this specific case. Now, if you take the case of the B matrix, the B matrix equals B1 into D plus B2 into 1 minus D, and we saw that B1 is B1 is 1 by L and 0 in this first case, which is D, plus B2 was 0 in this case. So, this becomes d by L and 0, d by L and 0, and the average small signal model, because this gets split into two parts as we saw, and only the steady state part comes into the portion here. Only the steady state portion comes in here, and all these parts, it will boil down to only d by L 0. That is, if you work out this equation, let me probably give you the we saw here that we get these matrices. Now, this A matrix is nothing but A1 into uppercase D plus A2 into 1 minus uppercase D. Only the steady state portion comes into the picture here. Likewise, here also you have B into uppercase D plus B2 into 1 minus uppercase D. So, that would be the expanded form of this. This having come from the simplification of this equation. So, if you work out in detail the simplification, you should land up with a simplified form for the small signal model like this, where A and B for the small signal model is like this, and that is what we have tried to apply here. In fact, I should probably make this one as uppercase directly to the final form. Here too, this would be the uppercase, and here also we have only the uppercase. Remember that this is the simplified version. So, once we have this, from here it is directly boiling down to this. Likewise, the C matrix, of course, the C matrix does not show any change, it is same as the C matrix, because this is the same matrix for both, and likewise the D matrix is also 0, it is the same for both the modes, the mode 1 and mode 2, and therefore, you will not see a change in that one. So, therefore, the averaged from the averaged model, we obtain the small signal model by applying these, values to these equations like this. So, the small signal model becomes x, in this case specific case I L hat V C hat derivatives equals 0 minus 1 by L, 1 by C, 1 by RC minus IL hat, VC hat plus D by L and 0, this would be for VG, VG hat plus something D hat. Now, what is this portion? Now, this portion is to be taken as you see this portion here, this portion of the derivation. So, it contains what is uppercase U? It is nothing but VG. What is uppercase X? IL and V naught. So, A1 minus A naught is 0 in this specific case. B1 minus B naught is as can be seen. So, in this case you have D by L into VG and this is 0 here. So, this is D hat. In some cases this and this are considered as inputs together as an input vector, and it can be rewritten in the following manner. IL hat, VC hat, IL hat, VC hat. This is derivative. I am putting a common derivative mark for both the variables together, plus now we have a B matrix and input. Now, let us combine both these together. We combine both VG and D as the input variables. So, you take this with respect for the D VG variable corresponding to VG input and this column corresponding to D input. So, this becomes the small signal model, which gives deviations about the operating point. All are deviations about the operating point. Every variable here you will see is a deviation about the operating point. So, the key here, likewise the output variable, which in this case is a trivial case where you have y hat, which is equal to C x hat plus d u hat plus du hat, but in this case d is 0 and therefore, it is just only C x hat or just 0 1 IL hat VC hat. So, this is all the output equation, but you should note that it all starts from the application of the steady state portion, small signal portion, to the original equation, average large signal equation, and to this average large signal equation, after applying this, multiply, that is component by component you multiply, and if there are small signal term multiplications, neglect them, and Ax plus Bu terms, set them equal to 0, uppercase x dot, this is 0. So, which means that only this exists on the left hand side. Then on equating them, you will land up with an equation which is like this. This is just having the small signal deviation. You have A x hat, where A and B are weighted with respect to the duty ratios which are steady state values. So, A and B contain only constant values for a given operating point, and then A1 minus A2 into the steady state value of the state vector. In this case, A1 and A2 are same, therefore, they cancel, become 0. B1 minus B2 into the steady state value of input u into D hat. D hat is again one of the control inputs, and then on simplifying it further, you will and applying it to for the DC-DC converter case, you will end up with the small signal model of the converter. Now, if you look at the small signal model of this converter, very important feature here is that it has not only Vg, variation about Vg as the input, it also has the variation of the duty cycle as control input, one of its control input. In fact, this becomes your major control input for controlling the output, the input current, and many other parameters. So, quite a significant parameter for you to control, which we will be repeatedly revisiting in the classes to come. Now, for you to practice, I would suggest that you try to apply the concepts that we have seen so far. They are actually not complicated. You just have 4 steps. First is obtain the large signal model, practice obtaining the large signal model for each mode of switch operation. Average the large signal model to obtain the averaged large signal model, and then from the average large signal model, as I said, the steady state portion of the model is set equal to 0, which basically means we are trying to subtract. So, essentially we are trying to subtract the steady state portion and simplify. This will give you the small signal model. So, practice this on the following circuits. We will do few more practice exercises. Take the case of the boost converter, which is nothing but the boost converter, and also take the case of the buck boost converter, which is like this. You have the load. This is the buck boost converter. Apply the methods that we just now went through in this class. This process of circuit averaging from the large signal model to the averaged average large signal model, remove the steady state model by setting the steady state portion A x plus B u equal to 0, and then obtain the small signal model of the converter. So, up to this point, try practicing. We will continue in the next class. Thank you.